Hello, hello everyone. So can you hear me?
Yes.
Okay, great. Right, so maybe we can still wait for some minutes to see if there is any other student to join. I have already, just as mentioned this morning, I have already sent your score of the project 3 and last week project 4. And I will grade project 5 and upload the midterm score as soon as possible within this week. And then you can make a decision, right? So based on the university policy to go to the PNF for the real grade, okay? And for the final project, I have already uploaded it. It's about the GPU programming for the matrix application. So I will finish the GPU lecture maybe next Tuesday and give some tutorial about how to use the CUDA. CUDA is a CUDA-based BLAS library. BLAS is a basic linear algebra library. It's about matrix, vector, vector multiplication. So you can implement yourself's matrix version, multiplication version, and compare with the CUDA. Okay, so the final project is implement your version and compare with the production level version. Okay, and I think everyone should be familiar with matrix multiplication, right? But how to increase the performance on the GPU platform, that's the focus of the project, okay? So maybe we should start today's lecture. So let's just recall some contents, what we learned previously. I think the key concept or concepts for the GPU is you manage the threads. It's not like CPU, right? CPU just use a OpenMP to set the threads number and it's transparent to you. You just put some pragmas there, right? But for the GPU, you have the different organizations of the threads, right? As I mentioned last week, for the threads, we should organize based on the thread blocks and the grid. So what is the thread block? I mean, it's straightforward to understand. So you have multiple threads, you group the threads into a block. So it is a thread blocks, right? We usually call it a block. And the multiple blocks, we group them together as a grid. And each time you launch a kernel, it's for a one grid, right? So if you look at this organization, for each kernel, right? For you launch each kernel, for example, vector addition, as I demoed previously. Each time you launch a kernel running with a one grid, so each grid will have a multiple thread blocks, and each thread blocks will have the multiple threads, right? And for example, here we use a 2D structure to organize the threads. So for each thread, you will have a 2D IDs, and for each block, you will have a 2D ID as well, right? And how many threads within one grid you can calculate. Okay, so that's the idea. And then you can map your thread. For example, for this thread, you will have a local thread ID and global thread ID, right? Because this is only for block 1.1. You can have the global ID. You can map the global thread, the thread with the global ID into the data block you want to deal with, right? Similar to matrix multiplication. I will mention it later, but the idea is that you use one thread to calculate each element's multiplication and accumulate the multiplication result into the final resulting matrix, right? It's similar to CPU version, but you will have a finer grain of the thread control, right? And this is a GPU architecture I introduced last week. So for, maybe I should use this mode, right? It's better to see. Okay, so for each GPU architecture, you will have a multiple streaming multiprocessors, right? SM means that streaming multiprocessors, right? For example, V100 has 86 SMs. So for each SMs, you will have a multiple CUDA cores, you have the shared L1 cache, and all the streaming multiprocessor share the L2 cache. So later we will introduce that this L2 cache, we usually call it global memory. And for this L1 cache within each streaming multiprocessor, we call it shared memory. Okay, so definitely, and I think obviously L1 cache has a higher throughput or performance than L2 cache. It's similar to CPU, right? But how much or how much faster of the L1 cache or shared memory is faster than the L2 cache or global memory? So we will give you some idea. Okay, but this is a high level hierarchy of GPU architecture and how we can utilize this architecture. So that's the idea of how you optimize your code. Okay, but let's first see some constraints or ideas or concepts of the GPU memory or the programming. Okay, and I think I introduced something here about a streaming multiprocessor, right? And for each kernel, the task will be divided into threads and grid blocks, whatever. I have already introduced this. And here is the important thing. So each grid and each block, you will have a maximum number of the threads you can launch. So that will cause some problem if you don't pay attention to this. So for example, vector addition. I will give you an extreme case that if you have a very large vector, but you cannot use such a large amount of the thread, right? You definitely should use one thread to deal with the several elements in the array, right? So that's the idea, but you should remember how many threads you can launch for one block and how many blocks you can launch for one grid. And each grid is for one GPU kernel. So that's the idea. And as I mentioned, every thread block, when you launch the grid or when you launch a kernel on a grid, each block within that grid would be assigned to a streaming multiprocessor. It's not necessary only one block in one SM, but we assign one block to a streaming multiprocessor. So for example, as simultaneously or at the same time, we can run maybe 16 or 32 blocks within one streaming multiprocessor. As I introduced last week, for each streaming multiprocessor, there would be a scheduler to schedule the block and schedule the warp, right? So here is a warp. The concept of warp is that within or inside the streaming multiprocessor, each thread block would be divided into the warps of the threads. And the warps consist of 32 threads. So why the warp concept is very important? Because this is the minimum unit that all the threads within one warp need to run the exactly same set of the instructions. Okay, two warps can run totally two different instructions, but one warp must run the same instruction. Otherwise, that would cause the warp divergence. The performance will significantly degrade. Okay, so that's the concept. And so as I mentioned previously, the number of the threads per warp doesn't matter with the GPU version, right? Even if we have a V100, even we have a very high-end GPUs or low-end GPUs, all of the CUDA programming model requires the one warp to have 32 threads. Okay, this is a determined thing. So let's just try to summarize something here. So the maximum number of threads per block is so for example, we use a Volta architecture here. Previously, as I mentioned, it's 512, right? But now we can have a 1024, and the maximum number of threads per grid is 65,535, right? So you can calculate how many threads you can use for one kernel or data or array, whatever you want to call. But you can consider, so if we do a calculation, how many data you can deal with if you only want to one thread to deal with one data point, right? For example, maybe 2 gigabytes or 3 gigabytes or 4 gigabytes, right? You can calculate the amount of the data size. And threads per warp, as I mentioned, it's fixed, it's 32, and maximum number of the concurrent warps per SM, just as mentioned. So it's not necessary one stream multiprocessor only run one thread blocks, right? But how many concurrent warps can be run within one stream multiprocessor is 64 with the 4 warp schedulers. So maybe we can do a calculation here. So for example, if you assume that, not assume, this is a fact. So 32 threads per warp. And if we assume there are 4 warp scheduler, right? So if we assume 4 warp scheduler, and I think this is the most of the cases for today's GPU. And then we have the 64 warps can be running concurrently per stream multiprocessor. So how many threads? It's a 64 times 32, right? 32 threads per warp, right? So that means totally that would be 64 times 32. That 2048 threads can be run concurrently in each stream multiprocessor, right? So then how many threads block can be run concurrently in one stream multiprocessor? It depends on how many threads you set for one block, right? So assume if I set, for example, if I set 512 threads per block, this is what we set for the vector addition, right? So how many blocks we can run concurrently within one streaming multiprocessor? That would be 2048 divided by 512. That would be 4 blocks, right? So what does this mean? So this means that, as I mentioned in the last slides, so each thread block would be assigned to one stream multiprocessor, but it's not necessary 1 block per SM, right? So based on our calculation, in this assumption, we can simultaneously run 4 blocks per stream multiprocessor. Okay, so I think the constraint for how many thread blocks can be run concurrently is not only based on the thread blocks itself. It's based on how many threads per block. Okay, and based on the assumption we have a 4 scheduler. So you need to notice that how many warp scheduler in the GPU architecture. For example, in the Volta architecture, there would be 4 warp scheduler, right? So what is a warp scheduler? So here, if you look at this streaming multiprocessor, so there would be a warp scheduler here. Can you see that? So this is the warp scheduler. You just schedule 32 threads onto the different CUDA cores, okay? And based on this assumption, at most we can have 4 blocks to running on one streaming multiprocessor here. Or you can see we can have the 64 warps to running simultaneously, whatever you want, right? So you can calculate equivalently. So that's the general idea, how you schedule these thread blocks or how you schedule warps on the stream multiprocessor. And as I mentioned, for the V100, that would be 84 stream multiprocessor. So you can pay attention, all the numbers here are updated or up to date. Because so far the most powerful GPU for the server or for the high-performance computing system is a Volta architecture. I think there would be some Turing architecture, but that would be for mobile system or for the mobile platform. Okay, for the server, it's still Volta architecture is the most powerful one. So you can think about these numbers are the up-to-date one. Okay, 84 threads per warp, 32, and simultaneously run 64 warps per streaming multiprocessor. Okay, so here are some numbers you can remember, or if you don't remember, if you want to do the project, you can just go back to check right? Because you want to make sure that the stream multiprocessor running the maximum concurrent warps, right? You don't want to set a maximum one. I mean, more warps than the stream multiprocessor can handle, okay? So for example, here are some other cases regarding the dimension information. So for example, if I set the DIM3, DIM block, dimension block 1688, and DIM grid as a 1661, and I launch the kernel, right? So that means 1024 threads per block and 32 warps per block, because the 32 threads per warp, right? So there would be 32 warps per block. And oh, this is just another case, right? For I use an example. Here is another example. So for example, here I specifically give you the number of the dimensions of block and the dimension of the grid, right? You can calculate simultaneously or concurrently. We can run 2 thread blocks per SM. Okay, and for example, we have the 84 stream multiprocessor. That means for whole GPU, we can run 168 thread blocks concurrently. Okay, and the one kernel with the 250 thread blocks. So that means we need to run at least 2 batches. But this is a very simple model assumption, right? I assume that all the kernels, all the blocks would be running at the same start at the same time and end at the same time. So I need to run several batches. So if there would be some interleave or maybe some gap or slack between the different blocks, then maybe 3 batches or even more, right? I don't know, but I just assume that if every block would be running with the same time, and each time 86 or 84 stream multiprocessor can only run 168 thread blocks. So at least I need to have 2 batches. Okay, that's the idea. And similarly, you can calculate the different cases, right? So for example, case 3, so 32 threads per block, that means 1 warp per block, okay? However, the maximum number of threads per stream multiprocessor is 32. That means you don't utilize the stream multiprocessor very well. That means your occupancy is not very high, right? You need to increase the threads number per block to increase the occupancy. So that's why usually people are setting 512 or 1024 threads per block, right? So you want to set as large as possible for threads per block. You cannot exceed 1024, but at least you want to close to this number. Why? Because it will depend on how many thread blocks per stream multiprocessor, and if you can utilize the resources as aggressively as possible, right? So that's the idea. So be careful. The point here is be careful about the specification of your GPU architecture and set the corresponding number of the threads per block and the number of blocks per grid. That's the idea. And everything can be calculated similar to this slide. Okay, so if you don't understand and if you don't know your GPU architecture, just go back to check your GPU architecture white paper. So for example, you can easily find the V100 white paper online. NVIDIA give you the white paper. You can check how many warps and how many stream multiprocessors and what is the maximum concurrent warps can be executed on one streaming multiprocessor, right? So 64 and 84, these 2 numbers definitely can be identified in the white paper, okay? The other thing I think is not changed too much. Maybe next version is still 1024, but I believe 84 and 64, that 2 numbers could be changed in the next version because they want to increase the number of the warps and increase the scheduler capability. Okay, so here I just show you that for the 1 stream multiprocessor, there would be a warp scheduler. So here we have 1, 2, 3, 4, right? 4 warp scheduler, and can execute the 64 warps at the same time. And here are some CUDA core and some, this is the L1 cache. So I will mention that later. So usually we will aggressively use the L1 cache as a shared memory. So this is very important. I will mention that later. And this is showing the Pascal GPU 104 GPU streaming multiprocessor that can be found in GTX 1080 graphics card. The exact amount of the cache and shared memory differ between GPU modes and even more different versions of the architectures. Okay, so that means you need to check the configurations. It's not like a Intel or AMD CPU kind of stable, because the CPU have been developed for many years, and most of the, for example, the cache line or L1, L2, L3 cache will not change too much, right? But for the GPU, it's not. So if you only compare several versions or generations before, the L1 cache or shared memory is much smaller than the current version, okay? So let's recall the vector addition. It's a very simple kernel, right? Everyone should know this kernel, because we have already talked about that. And the problem for this kernel, right? So is there any problem for this kernel? So for this kernel, we only, for example, previously I think I only launched 10,000 or 1 million. I don't remember, but I remember I launched a few numbers of the elements per array. So it's not a very large number. So if n is a very large number, right? Previously, I remember I launched maybe 10,000 or hundreds of thousands. I don't remember. But if I launch a very large number, and this number would make the number of the elements exceed the maximum number of threads you can use, right? So this is a problem you would introduce to your kernel. So if you only write the kernel like this way, so we need to handle some extreme case, right? So first, we need to put the maximum block count. So how many thread blocks per grid, right? So we have the maximum number, and the number of the thread per block is 1024, right? We put those two numbers here to tolerate some extreme case, right? So if, for example, you calculate the number of the, you not calculate the number of threads per block, you calculate how many blocks per grid, right? If this number is larger than the maximum block count, then you need to handle this case, right? So here, I just use a minimum function, min function, to compare the maximum block number and if you use the array size divided by the thread per block, you will get some block number. Previously, we just use this number for the number of blocks, right? But now, the problem just I mentioned, so if you have a very large number of the elements per array, right? How about the case? So you need to deal with this extreme case. And then you use a minimum or the smaller value, right, as a block count. That means if your number of the blocks is exceeding the 65 and 535, this number, you would just use this number. But the problem is that you don't have enough thread to handle all the elements if you assume one thread, if you assign one element to one thread, right? So that means each thread needs to handle several points. So how we should change our kernel? So that's the idea. The idea is just simple. You just ask the thread ID each time to increase by how many threads per grid, right? For example, the first half maybe can handle the extra points. So I remember one student asked the question, right? So if you have maybe just one more point than the maximum thread you can handle. So my suggestion is that you don't want to do this, because most of the thread would just execute another loop without doing anything, right? So maybe you can reduce your number of threads to half and make your thread block workload balancing, right? So I'm not sure if I remember this is a good question. sent by students last week. So for example, now what is the maximum thread number we can have? It's a maximum number of threads for V100 GPU is 1024 times 65 or 60, 36 or 65. Let me double check. Okay, 35. And how many threads, maximum thread we can have? I remember the student calculate last lecture. So for example, not for example, I just calculate the number here. So for example, if I have a maybe plus 10, right? I have such amount of elements, okay? So how I should assign the elements to the threads? I don't want to just use the first, all the threads to deal with the first part of the elements, and then I do another batch, right? Because most of the threads will not do anything, but just do another loop. So the more efficient way is you just use half, for example, maybe such amount of the threads, right? And each thread would execute twice. I think this is a smarter way to do that, right? So I remember this is a question asked by some student last week. And here is just what is our solution for the procedure code, right? Based on the procedure code, you can notice that the first batch and then the second batch and third batch, right? Each thread would just do a loop until its index exceeds the number of the elements in the array, right? So you can, so the key point I'm saying here is that you need to balance the workload and the number of threads, okay? You don't want to have some thread doing nothing, some threads are busy, right? Just trying to balance them. This is just a key idea of the parallel computing. It's not only about the GPU or MPI or OpenMP, right? You just want to all the thread to have the same or similar workload, right? You don't want to have some workload imbalance. Okay, and the minimum extension to C and C++. So that's the function you need to, I mean, that's some extension you need to put into the function. Okay, so for example, global. Global means that the kernel callable function from the host. That means the host can only call this kernel, or not this kernel, this function, right? Yeah, this is also a kernel, but this is a function. Okay, so the kernel function you need to define as a global extension, right? But for the device, so every similar to the traditional C or C++ programming, you can have a main API, right? For example, vector addition. But within vector addition, you can have several separate functions. But all the other functions is not callable by the host, needs to define with the device extension. Okay, I'm not sure if I explained clearly, but the idea is that only the function defined with the global can be called from host. If you remember, for example, let's just look at this code. So this is the main function, right? I call the vector addition kernel, right? So this kernel needs to be defined as a global with a global extension, okay? But similarly, I can maybe add more functions on the device to be called by this kernel function, right? I can define another, for example, I count how many elements per thread block, right? So whatever, I just arbitrarily define another function, and then that function is not called by the host, it's called by the device kernel function. Then I need to add its extension as a device instead of global. Okay, so this device code is this device extension represents the function that would be called by the device and only callable on the device. For example, if you call this function from host, then the compiler will give you some error because this is only the device code, right? This is a global code. That means the code and function can be called from the host. Usually we call it a kernel function, right? And also similarly, we can define the variable for the device and the variable for the shared memory, okay? So the device memory means the global memory, and shared memory, just as I mentioned, is L1 cache. I will give some detail later, okay? So here are some extension or basic extension you need to remember. For example, in your final project, if you want to define your own matrix application or DGEMM, right? We usually use the DGEMM, means the double precision general matrix application, right? If you define your own DGEMM for the kernel, you need to use a global, right? Global void my DGEMM, right? So if the DGEM will call some other function only in the device, then, for example, you generate some matrix initialization, right? You can define a device function, but usually we will generate the data on the CPU, right? I'm saying that if you want to do something on the GPU instead of the kernel, you need to define it as a device function, okay? And yeah, this is what you have already be very familiar, how launch the kernel, right? You have to use this extension to the C and C++. You just add something here, okay? And for the dimension, it has a thread ID, block ID, and the block dimension, okay? And this is the synchronization. So I will introduce the different synchronization scheme on the GPU. So first, if you set the synchronization threads function here, that means you set a barrier within one block. Okay, so this is a very important point. So here, the synchronization or barrier is only for one thread block. It's not for global, okay? But if you call two kernels, minimize and dot, then each kernel will have an implicit barrier across all the threads. So that means you have already finished this kernel, right? Everything has been done. So you will set a global barrier to synchronize all the threads blocks, okay? But for this one, you only synchronize or set a barrier for one block. So that's a very, very important case. I have some students working on the GPU project, and nowadays, we have some advanced techniques to synchronize across the blocks, but this is a very late techniques. So from the CUDA developed from 2007 or 2006 until 2017, there is no technique that can help you to synchronize the threads across the block. It's not possible. If you want to synchronize across the block, you have to divide your code or kernel into two halves, right? First half and second half. And between these two halves, you would have some forced synchronization across the different blocks. Okay, so this is a key idea about how to do a synchronization. And next, so is that possible to interleave the blocks, or if you want to blocks to have some synchronization, just as I mentioned, blocks may coordinate, not synchronize, okay? And independence required to give scalability, because you don't want to synchronize across the different blocks. But as I mentioned, now there is some more advanced technique can help you to do that. For example, is the cooperate thread synchronization. But this is a very late technique, okay? For you to generally understand the GPU programming, you can think about the blocks cannot be synchronized within the kernel, okay? After the kernel, all the blocks will be synchronized. And if you want to synchronize blocks, please partition your kernel into the two halves, right? For example, if you want to synchronize the first part of the minus and second part of dot, you just put the two parts into two separate kernels, right? You can, for example, you can calculate the minus b, a minus b is equal to c, right? After that, you just want to do some dot c times c, right? You just put them into two kernels. And as I mentioned, this is a purpose, design purpose for the scalability, and your code or same piece of the code can be run on the different version of the GPU architecture or GPU device. That's the key idea. The CUDA or NVIDIA doesn't want you to re-implement your code based on their development of the architecture or the resources, right? For example, for the different version of the GPU, they have the different number of 3 multiprocessor. Now I think we have the 84, right? But you can see that the code can be adapted to all the architectures, and the performance would be increased even if you don't change the code, okay? Because the number of 3 multiprocessor increase and the thread blocks bring the scalability. So that's the key idea. So here are some, just some, it's a recall, right? We have already mentioned that, but this is the 2 or 3 most important concepts in the GPU programming. So if people ask you, what is a stream multiprocessor, what is a warp, or what is a warp divergence? This is a very basic case. If you don't know that, that means you are not familiar with the GPU programming. So the stream multiprocessor, as I mentioned, it's a basic computing unit, right? Schedule different blocks, and each stream multiprocessor can run multiple blocks and multiple warps. And what is a warp? As I mentioned before, it is a unit of 32 threads, okay? And what is a warp divergence? It is when your 32 thread will not execute the same or different instructions, then the warp 32 thread would divide into the multiple pieces and sequentially run your code. Okay, so then that's a bad idea, just as you use a 1 thread to execute something, right? You cannot utilize 32 threads efficiently. Okay, so that's some basic idea. I think let me quickly start with part 3, introduce the GPU memory system. And why this is important, because as I mentioned before, GPU is architecture designed for high throughput computation, right? For CPU is a low latency, for GPU is a high throughput, okay? And how to utilize the GPU features is about how you can utilize the different levels of the memory system, right? As I mentioned, we have the shared memory, we have the global memory, and we have L1 cache, we have L2 cache, okay? So think about something related to CPU, but the throughput is much higher than CPU. So for CPU, I think it's only about several tens of gigabytes per second for the main memory or for something. But for the GPU, we have almost 1 terabytes per second for global memory, or 900, accurately speaking, it's 900 gigabytes per second for the global memory. This is only for global memory. If you want to use a shared memory, it could be 2 or 3 terabytes per second. So this is very impressive throughput, right? So think about your CPU memory. You only have tens of gigabytes, but for GPU, you will have 900 gigabytes per second. That means if you have a lot of operation, read and write memory, you should think about the GPU, right? And also when you kernel have a lot of parallelism here, right? So here is some recall. We don't need to look into this size here. And for the different GPU architecture, as I mentioned, it developed very fast, very, you know, every year or every maybe half year, there would be some new architecture or generation would be released. And for the different version of the architectures, there would be a concept called the computer capability. That means some generation or some version of the GPU, they share the same set of the capabilities, okay? For different capability, you can support the different feature. For example, as I mentioned, generally speaking, you shouldn't synchronize your computation across the blocks, right? But after the capability of CUDA 9 or CC7.x, then there would be a capability to synchronize across the blocks. So if your architecture, if your GPU is not it doesn't belong to that a CC, then you cannot do the synchronization across blocks. Okay, and for compilation, you need to specifically give the compiler an idea what is the CC of your GPU, right? And then the compiler would introduce some feature into your compiled code. Okay, so CC is a general idea is how powerful of your GPU device. Okay, for some details, you can just check the CUDA CC online. Different numbers. Now I think is for 7 point something. So this is the GPU card, right? And we can see the different GPU cards, and you can see the streaming multiprocessor is developing very fast, as I mentioned, right? So for the old GPU, you only have 14 streaming multiprocessor, but now you have 84, right? And as I mentioned, GPU is developed for the high throughput. The CPU is developed for the low latency, right? How low is the latency for CPU? So for CPU, memory latency is about 100 nanoseconds, and for the CPU arithmetic instruction latency is only about 1 nanosecond. But for the GPU, you can see the arithmetic instruction latency is about 10 nanoseconds, and the memory latency is about 300 nanoseconds. And the GPU running on a low frequency, right? Because as I mentioned, you can maintain low frequency, but a higher parallelism to increase the power efficiency, okay? But you can pay attention that the latency of the GPU is very high. It's much higher, 10 times or 3 times higher than CPU. So even if in a CPU, we talk about the cache and the register blocking and cache reuse, right? That means we want to hide the latency. We want to reduce the penalty if you access to the data in the wrong location, right? So for the GPU, it's even more important, because if you don't utilize the memory efficiently, you will pay much more penalty for the latency, right? So this is the idea. You need to think about how to smartly use the memory. But for the GPU memory, usually we only talk about shared memory and global memory. So we have other some memory concepts. But when you program your first CUDA code, you just think about how to use shared memory and global memory. So I will give you some example code later. This is a GeForce GTX Titan GK110 based GPU. So you can see that the computing throughput could be the 5 terabytes per second for the single precision. It's very high. And the global memory bandwidth is about 336 gigabytes or 84 gigaflops per second. So this is the old version, but it's still very high, right? As I mentioned, the CPU only have a 70 or 80 gigabytes per second for the memory, but for the GPU, you have hundreds of the memory bandwidth. Okay, so I emphasize, or I repeatedly emphasize the throughput. The point is that in many cases in the future, if you do something related to GPU acceleration, or you have some job, you have some research to do with a GPU, the first thing you need to think about is if your computing kernel is suitable for the GPU device, right? You shouldn't put something very unsuitable into the GPU. Then you first need to think about what is the bottleneck of your computation. If your bottleneck of your, for example, if your bottleneck is based on the memory speed, right? You can test. Previously we showed some flying figure. If you can think about that. If your kernel, right, mostly spend the time and in the read and write data, or just read one data, but you don't use that for several times, that means your code is highly memory bounded, right? If your code is highly memory bounded, GPU is a very good choice for your case. Assuming there is some parallelism, right? So if it's not a parallelable code, then don't talk about anything related to GPU or OpenMP. So first, you assume your code is parallelable, and then what is the best fit for the GPU? is that your code has a read the data only once and use the data maybe only 2 or 3 times. So then that means you don't have a high reusage of your data. Then your data would be, or your program, your code would be memory bounded. Okay, this is just a general idea. So the GPU is very I/O limited. I/O is often the throughput of the bottleneck. So here I/O is not the memory bandwidth. This I/O means you transfer the data from GPU to CPU. Okay, so don't be confused about this I/O. This I/O is not the memory I/O. Memory, we usually call it a memory transaction or memory bandwidth. If we talk about the I/O, means from the GPU in, from GPU output the data or read the data to GPU. That means we transfer the data between GPU and CPU. Okay, so still remember your CUDA programming model. We have 7 steps. The first or second step is after you allocate the memory, you copy the data from host to device, right? So that step is very time consuming because the I/O is very limited. Even for today's PCIe 4 or maybe future 5, it's only about 10s or maybe 20, or I remember it's not over 30 gigabytes per second for the GPU CPU data transfer. Okay, compared to the memory bandwidth, the communication between CPU and GPU is very limited, right? Okay, so here is some basic idea, and what is a cache? As we previously mentioned, everyone knows a cache. Cache is a chunk of memory that sits between the larger pool of memory and the processor, right? You have the different level of a cache because you don't want to every time access the data from the memory or from the disk, right? The cache is a concept that sits between the larger pool of memory and the processing unit. Okay, we have a different level of the caches, right? So when memory is requested, actual memory near the requested memory is read into the cache. So here's the same concept as the CPU. Amount of read is the cache and memory pool specific. So all the things are similar to GPU, to CPU, memory, cache hit and cache miss. Everything is similar, okay? And for the GPU memory breakdown, actually we have the registers, shared memory, constant memory, texture memory, local memory, global memory, L1, L2 cache, and read-only cache. And for this class, I don't want to confuse everyone. We just focus on 3 or 4 most important caches and register for the GPU. Okay, we similar to CPU have the register, but for the GPU register, it's much larger than CPU register. And this is a very important important point. I will mention it later. And we have the shared memory. I mentioned that several times. Shared memory and global memory, okay, and local memory. So here it's a diagram to demonstrate the memory scope. So as I mentioned, for each stream multiprocessor, okay, you will have a shared memory. The shared memory is shared by thread block, per block shared memory. And all the thread, all the grids can access to the global memory, okay? And for the local memory, it is shared, it's not shared, but it's owned by each thread. So from the high level to lower level, local memory belongs to thread, and shared memory belongs to each block, and the global memory belongs to each grid. That's I don't think this is difficult to understand, right? So if you have already established the concept of the thread, block, and grid, this is just some corresponding relationship. So for the local memory, it's for one thread. For the shared memory, it's owned by each block. And for the global memory, every blocks can access to global memory. And you can think about each memory will have a different speed, as I mentioned. Global memory, for example, V100 have hundreds of gigabytes per second. This is some terabytes per second. This is even more or larger, okay? So let's first talk about the global memory. Global memory is separate hardware from the GPU core containing stream multiprocessor caches and extra. So the vast majority of the memory on GPU is global memory. So for example, if you, everyone should previously know some game and playing some gaming, right? So if you have some laptop or desktop needs to have a higher or larger GPU memory, then that means maybe you can play your game more smoothly, right? So this usually people are talking about the GPU memory. For example, you purchase one NVIDIA GPU card with 4 gigabytes. So this 4 gigabytes is a global memory, okay? So this is a global memory. Usually is a specification in your GPU card, right? You purchase a Titan X GPU with the 8 gigabytes. So, but usually for your laptop or desktop or for your personal computer, usually we only have maybe 4 gigabytes, right? Or sometimes 2, maybe for the laptop is even 1 is possible, right? But you can seldom see some larger memories than 8 or 12, right? Because even for our server system, for example, the Panther-Heat system, you are trying to do your project or the DMC cluster, all the GPU there only have 16 gigabytes per, not only have 16 gigabytes global memory per GPU card. This is because of some design principle. It's very hard to design a large amount of the memory for GPU. Because some people may know the concept of NUMA or some architecture. If the parallelism of your core, if number of the core is very large, it's very hard to design a large shared memory or global memory. Okay, that's the key point. So today, I think there are a lot of research about you are trying to use more data on the GPU, but the GPU memory is the limit. So nowadays, I don't think CPU memory is a problem because, for example, for CPU node, we can even have 400 gigabytes or 500 gigabytes, right? Sometimes close to 1 terabyte, 700 gigabytes. So it's very large. And for the GPU, you can think about it's 10 times smaller than the CPU memory, right? Memory size. So the GPU, the challenge is that GPU is very fast, it's very powerful, but the memory is very limited. So you need to handle the GPU memory very carefully, okay? But all the memory size we talk about is about the global memory, okay? So we will show some data for how large is the shared memory. It's very small, but for the global memory, it's much larger than shared memory, but it's still relatively small than the CPU memory. So this is the idea, okay? So if the data cannot be fit into the global memory, you are going to have processes in chunks that do fit in global memory. So each time you only read several chunks of the data into the global memory and process the data by chunks, okay? So you can see GPU usually have half gigabytes to 24 gigabytes of global memory. So 24 gigabytes memory is can be seen in the market, but it's very expensive. So because you are now online, you can just randomly search the V100 with 24 gigabytes of memory. That would be much expensive than 12 gigabytes or 8 gigabytes, right? Because design a large memory system for GPU is very difficult. So the price is very high. I think it's $9,000 or something. I'm not sure if the price changed, but previously when I searched, I think about this is really expensive for one GPU card, okay? So the global memory latency, just I mentioned, is around 300 nanosecond on the Kepler and 600 on the Fermi. So even if the latency is improved, but it's still much higher than the CPU, okay? So here the red lines are the global memory. So from the picture, you can see that the global memory is not like a stick, right? Similar to the, unlike the CPU, right? CPU is just some stick put into near the CPU. But here the GPU memory, because it is an on-chip memory, right? It has a very high throughput, but it's also limited size. So accessing the global memory, so global memory I/O is the slowest form of the I/O on GPU, except for accessing the host memory. Okay, so even I mentioned global memory is the fastest. The global memory I/O is the slowest for the GPU device itself. But you can still think, I just try to repeat again, but you still think that this is a very high number. For example, 800 or 900 gigabytes for the global memory bandwidth, but you only have a 10 gigabytes for the GPU, CPU data transfer, right? The gap is very large. And because of this, we want to access global memory as little as possible. Access patterns can play nicely with GPU hardware are called coalesced memory access. So here is another very important point I want to introduce maybe before the end of today's class. So what is memory transaction pattern or coalescing? You should pay attention to your code when you try to access the global memory. Okay, so here is the memory transaction and the coalescing concept. So memory transaction means that each time you can trigger a transaction of one memory transaction, it only reads 32 or 128 bytes. It has some unit, right? You cannot just read 1 byte from the memory. Even if, for example, it's similar to the cache line. You still remember? It's similar to a cache line. I want to read the A1, right, or A0, the first element in the array A. Then I need to at least read a cache line, right? So that's the concept of the CPU from the memory to the processor. Similar here, if you want to access the global memory, you trigger a transaction. This transaction will be based on 32 or 128 bytes. Okay, transactions are aligned to its size. Transactions are always the read after write, fully read write. Okay, so I think the coalescing concept is the most important concept for achieving a good performance using the global memory. So what is the coalescing? So coalescing means that adjacent thread can share the transaction. And the degree of coalescing is the number of the bytes requested divided by number of the bytes read. So more memory read than use, the performance will be penalized. So this is some concept very abstract. Let me show you a quick. Let me show you a case. So for example, I have the 32 threads request 32 aligned or permuted 4-byte words. All addresses fall into the 4 segments. So here you can see for 32 threads, I read aligned 4-byte words, right? So that means you can think about how many transactions we need to use based on our assumption. Each time you can only read 32 or 128 bytes per transaction. So for example, this is the one from 0 to 128. This is 128 to 256, right? You have the 32 threads. Each thread would read 4 bytes. So that means you need to read 128 bytes, right? So if we assume that 32 bytes per transaction, so if you're starting from the 128, this point, you would only read 4 transactions, right? You only need to use 4 transactions because each transaction is 32 bytes, right? 32 times 4 is 128. Also, you need to read 128 bytes. So that means all the data read by the 4 transactions will be used in the calculation. Am I right? So even if this is a very random, maybe this thread reads this thread reads that, this thread reads this thread reads that, it's okay because all the data still be used 100%, right? So that means your read is a memory coalescing. The bus utilization is 100%. But we can give some not very good case. For example, the 32 adjacent thread requesting 32 aligned 4-byte words. It's a same assumption. But all the addresses fall into the 5 segments. For example, you are not starting from 128. You're starting from maybe 96, right? And 96 means that you finished before the memory location before 256. That means you need to spend 5 transactions for read 128 bytes, right? But you only use 128 bytes. So you can calculate the utilization, right? That would be 4 transactions is what you really needed, but you actually spend 5 memory transactions. So that means the bus utilization is 4 divided by 5 is 80%, right? This is not very bad, but this is not good because this is not aligned with 32. Okay, and we can have some bad case. This is some very commonly seen case. All the threads would request the same memory address. Okay, for example, 32, one warp, right? Requires the same 4-byte word. The address will fall into just one segment. Okay, so the warp will require 4 bytes, but 32 bytes transferred. So that means your bus utilization is what? Is 4 divided by 32. So it's only 10%, or actually it's a 12.5%, right? For example, all the threads, no matter each thread ID, you just access the A42, right? So this is not good. So think about the idea for the GPU programming, you should have some aligned memory access. For example, ID is equal to 0, you access the data 0. ID is equal to 1, you access the data maybe to 2, right? You have to make sure that the memory would be coalesced or aligned. That's a key idea. You shouldn't ask all the memory, all the warps to access the same memory location. But maybe your algorithm limit or your kernel limit, you have to have some step, right, to read the same location of the data. Then we have some other technique. For example, you can prefetch the data, right, and use that prefetched data to copy to the different location, right? You can think about the idea. You need to avoid ask all the thread to read the same piece of the data or read some address that are not aligned. That's the general idea, okay? So this is a very classic case. For example, this figure is straightforward for you to understand. This is a very good 100% bus utilization. We call it the memory coalesced, okay? So this is not fully coalesced, but it's okay. For this case, it's very bad because the utilization is very, very low. Okay, and sometimes, as I mentioned, maybe each time one thread need to handle 3 elements. Then, for example, this is thread ID. You just, every time you assign 3 times TID element to this ID, to this thread, right? And then your utilization would be, for example, this is a very simple to calculate because every element, I mean, every transaction, you only use 1/3 of it, right? So you assign 3 elements to one thread. That means the bus utilization would be only 1/3, right? 33%. For example, in this case, you will have a transaction of 12, but you only have 4 transactions or maybe 128 bytes are really used in the memory access, okay? So this is the idea about how you can make your global memory access as efficiently as possible. You should make sure your memory access is coalesced or coalescing, right? Coalescing memory access. And here is just a simple case, how you can define a structure of array or array of structure. So which way is better? Use structure of array or array of structures? So if you use a structure of arrays, right, you can make sure for each array, you will have a memory coalescing. But for the array of structure, for example, here is not A 3 times ID, it's A TID, B TID, C TID. These 3 elements are close to each other, right? It's like 3 times TID. That means every time you need to jump 3 elements to access the next element in A, right? Because the A TID, B TID, C TID are close to each other. Next element in A is A TID plus maybe plus 3, right? A TID plus 1, but actually the address is in the the next three locations for the previous A element, right? So it told us we needed to use the array structure of array instead of array of structures to represent some data here. Okay, then you can use a memory coalescing scheme to increase your global memory transaction. Okay, so here is what I mentioned. So you need to make sure each time you read the data is coalesced. This way is not good, right? This way is good. Okay. So I think that's it. Or maybe here are some other cases, the more examples, right, to demonstrate the memory coalescing is different cases. Okay, so I think that's it for today's lecture. It's for the we have introduced all the concept for CUDA programming, and we started introducing the memory concept and how to utilize the global memory. And for shared memory, we can discuss next week. And I think during the meantime, you can start working on your final project. I give some time to you, almost a half month, right? So you can tune your performance to be as close as possible to the CUDA version. Okay, and I think all the concepts we have introduced are enough for you to start the programming CUDA code. Okay, so the other concept about how to optimize, but you can program your naive version. I think during the meantime, we learn the CUDA programming. Okay, so any question regarding today's lecture or other stuff you want to discuss?
Yeah, I just wanted to make sure I understand the project. We're going to implement like the Kublas version of matrix multiplication, and then we're going to like time that, and then we implement our own CUDA matrix multiplication, and then we're just trying to get that to be as good as the Kublas version.
Yes, for Kublas version, I don't think you need to implement. You just call, right?
Yeah,
it's
a function.
Yeah, you just call the CUDA function, just one line, and just initial some data. That's fine. And for your version, yes, please implement your version and optimize the performance as good as possible, and compare the difference between your version and CUDA's version. But the most important thing is that you need to verify the correctness of your code, right? You just compare your result with CUDA's result. You show the difference. If it's 0, that's fine, right? And measure the time of your version.
All right, thank you.
Mm-hmm. So any other question? So for your version, you can you don't need to use shared memory, right? At the beginning, you just implement a global version, right? I will post some slides, the last slides of our class. It's about how to implement shared memory version. But even if you don't use a shared memory, as I mentioned, you can still implement a global version, right? A global memory version, right? And just make sure you have the good memory coalescing. Right, then your performance will be not very bad. Could be maybe 50 or 100 times slower than CUDA. It's fine. After you implement a shared memory, maybe only 10 or 5 times difference, right? But try to start as soon as possible, because this is your first time to implement CUDA. I can think about some difficulty, because CUDA programming model are sometimes very different from CPU. You need to handle the data copy back and forth very carefully. Otherwise, you will have some failed kernel. Okay, so any other question? As I mentioned, I will upload the midterm score within this week and grade the project 5 as soon as possible. And then I think that's it for this semester, right? I'm considering if I still need to post the final exam as a project. Maybe we don't have enough time. So if we don't have enough time, we just skip the final exam, the question. Because previously I mentioned I want to use that as an extra project, but it's fine because it's only about the 3 or 4 questions. I want to give you more time for the final projects, okay? So that's the current plan. Okay, so if you don't have any questions, that's it. You can send me an email if you have any questions regarding the final project and the grading. So I generally grade your project 3, I think everyone did good for the MPI, but still some students don't know how to run the MPI code with the multi nodes, and they didn't test the code. So I don't know where is the confusion, but if you don't know, just send me an email. Okay. Okay. So thank you everyone for attending. So see you next week. Bye bye.